O, teraz. Dzień dobry Państwu. Welcome everyone. So it is my great pleasure to welcome all of you, but especially our lecturer, Professor Maksym Radziwiłł, who would deliver us the talk on the topic of the modern development in the analytic number theory, as far as I understand. Professor Maksym Radziwiłł is a very well-known mathematician originating from Poland as well. So he finished his high school in Warsaw, as am I right? And then he moved to Canada, where he continued his studies. And after finishing his PhD, he had already a big career, being affiliated in many universities in Canada and the States, like McGill, Stanford. He was Rutgers, Caltech. At the moment, he is in the University of Texas in Austin. He was also awarded with many distinguished prizes. Let me mention one of them. That was one that is devoted to Polish mathematician, the highest one, so Banach Prize in 2019. But he also received a number of prestigious prizes. Let me mention the last one. This was the Cole Prize for also achievements in number theory. Probably it's not the full list, and more prizes will be awarded to him, hopefully. So this is the next lecture within the under the name of Professor Łojasiewicz, who was active at our university for his whole professional career. Professor Łojasiewicz died in 2002, and the tradition of the lectures goes back to 2010. Actually, in 2019, when we met, we made appointment that Professor Maksym Radziwiłł would deliver us the lecture in 2020, but because of the different circumstances, it couldn't happen, as you may guess, but fortunately, at last, it will come true. So I welcome you all, and now I will ask our rector, Professor Piotr Kuśrowski, responsible for research and science, for a few words on this occasion. Thank you.
Bardzo dziękuję, panie dziekanie. Ja przepraszam, nie jestem tak dobrze przygotowany jak pan dziekan do tego wystąpienia. Witam bardzo serdecznie naszego gościa, który znalazł czas i możliwość, żeby do nas dołączyć, i wszystkich państwa tutaj zgromadzonych na tej sali. Bardzo się cieszę, że kolejny wykład imieniem Stanisława Łojasiewicza będzie wygłoszony przez tak znakomitego gościa. Tym bardziej się cieszę, że zdecydował się na to, żeby również poprowadzić warsztaty dla naszych młodszych kolegów. To jest bardzo ważne z punktu widzenia rozwoju naukowego, dydaktyki. Bardzo się cieszymy z tego powodu, że takie świeże spojrzenie matematyczne, niekoniecznie tutaj z naszego kraju, ale z zewnątrz, będzie wykorzystane przez naszych młodszych adeptów do tego, żeby się rozwijać naukowo i powiększać swoją wiedzę. Proszę Państwa, też chciałbym nawiązać do tego, że w tym roku mamy szczególny rok kopernikański. Mija 550 lat od urodzin Mikołaja Kopernika. Z tego powodu świętujemy bardzo hucznie w kraju, również na Uniwersytecie Jagiellońskim. UJ wespół z Uniwersytetem Mikołaja Kopernika i Uniwersytetem Warmińsko-Mazurskim organizuje Światowy Kongres Kopernikański, który w przyszłym tygodniu trafia do Krakowa, i tutaj będziemy przez 3 dni uczestniczyć w różnych imprezach, głównie wykładowych, które są poświęcone tej działalności ekonomicznej i teologicznej Mikołaja Kopernika, bo ten fragment aktywności przypadł w udziale Uniwersytetowi Jagiellońskiemu, który ma rozwinąć te myśli. Ale myślę, że ten wykład, na którym dzisiaj jesteśmy, to jest pewnego rodzaju wydarzenie satelitarne, które jeszcze mocniej podkreśla to, że Mikołaj Kopernik był studentem uniwersytetu, ale studentem, który głównie zdobywał tutaj wiedzę w zakresie astronomii i matematyki. Wówczas ta szkoła Akademii Krakowskiej, właśnie astronomiczno-matematyczna, była szczególnie mocna i przyciągała młodych ludzi, żeby kształcili się w tym kierunku. I myślę, że to dzisiejsze wydarzenie, ten dzisiejszy wykład, to jest właśnie podkreślenie też między innymi tej aktywności, tej roli Mikołaja Kopernika i bardzo się z tego powodu cieszę. Bardzo dziękuję. Zapraszam na uniwersytet, jeżeli pan doktor kiedykolwiek będzie miał sposobność, żeby do nas dołączyć. Myślę, że mury uniwersytetu są zawsze otwarte.
Czyli używam Okay, to dziękuję za zaproszenie i przejdę na angielski. So I will talk about analytic number theory. It's a topic with a great representation by Polish mathematicians, so Iwaniec, Szindzel, Kaczorowski. And despite a very good representation, I don't think it is very popular in Poland. It's somehow my impression, maybe I'm wrong. So I would give a perspective on analytic number theory. It's a very personal perspective. So I will talk about some things that I find important and my view of the subject, but I will not talk about all the important things in the subject. So it will be a very personal perspective. And my perspective on the subject is that it's really tied with the Riemann zeta function. So the Riemann zeta function was defined by Riemann. It's this function is defined initially only for a real part of S bigger than 1, where it converges. But you can actually analytically continue this function to the whole complex plane. And then this function has two properties. One property, which is more immediate, is the so-called Euler product. Oh, there is a typo, -1 is missing here. So this Euler product property comes from the fact that there is unique factorization into primes. So you can, because you can write every integer uniquely as a product of primes, you can convert the sum into a convergent product over the primes. With a typo here, a -1 is missing. And there is a second property called the functional equation, which is not as obvious. The property is that if you properly normalize this function, it has an equation around the line 1/2, relating s with 1 minus s. And this is somehow much less obvious where this comes from. So it turns out that this functional equation is actually equivalent to Poisson's summation formula. So if I assume Poisson's summation formula and I take a Gaussian kernel, then I can actually derive the functional equation by integrating along this Gaussian kernel. But on the other hand, what you can do, you can also take the functional equation and you can integrate it against some kind of Mellin transform, and then you get Poisson's summation formula. And what is Poisson's summation formula? What is its meaning? Poisson's summation formula comes from the fact that the integers form a lattice. This is actually what makes it possible. So what Poisson's summation formula captures, it captures that the integers lie on a lattice. And when you have this perspective, you realize that the second property of the Riemann zeta function, the functional equation, is the fact that the sum of integers is an integer. So this is the fact that the product of the integers is an integer. This is the fact that the sum is an integer. And what we conjecture that these two properties alone should be responsible for the Riemann hypothesis, which claims that all of the zeros of this function are on the line 1/2, with all the non-real zeros. And so this is one of the big mysteries of mathematics. Why just these two properties force the Riemann hypothesis? And then maybe a more elementary way of stating the Riemann hypothesis is a statement just about primes, is the statement that the number of primes up to x is actually quite predictable. It's an integral of from 2 to x of this function with an error term that is square root of x. And this error term square root of x is basically optimal, because if the primes were just a random sequence, if being prime was a random event, then you would expect almost surely this type of error term too. Something with square root of x, maybe log. So what the Riemann hypothesis asserts, it asserts that in terms of counting, prime numbers are completely random, right? But even though they're random, they come from something that is very nicely structured and has a good reason for its truth. And so when I think about the subject of analytic number theory, when I look at a paper or a topic, I typically try to think what property of the Riemann zeta function does it use the most? And this actually orients me in the subject. So roughly speaking, we have a number of subjects which really depend on the Euler product. So those are subjects that fit into multiplicative number theory. So this is when you study prime numbers, or if you wish to study the zeros of the Riemann zeta function, or if you want to study factorization of integers, then you definitely be using mostly the Euler product. On the other hand, if you want to study additive properties, let's say you want to study when is an integer n, in how many ways can you write down an integer n as a sum of k cubes? This is Waring's problem. Or if you want to study points on varieties, something known as Manin's conjecture, for example, then definitely you'll be using a lot of Poisson summation formula. And this is also related to exponential sums. You can think of exponential sums as sort of Fourier transforms of these counting problems. But there's also a big surprise here. So you can also try to generalize Poisson summation to non-abelian settings. And this leads to the so-called Langlands program with trace formulas and so on. And this is something that we use a lot in analytic number theory. We use these non-abelian generalizations to actually say things about the integers. This is maybe something that is not as widely emphasized as it should be. And these, of course, interact. I mean, often you can, these subjects interact, but maybe not as much as I would like them to interact. Okay, and so in both areas there have been a lot of advances. So I just want to mention some of these advances along the way, but mostly I want to mention how we think about the subject, kind of the mental model that we have about the subject. And what I want to do, I don't want to start with the primes. Everybody always talks about the primes. So I actually want to start with Poisson summation formula, because it's a somewhat neglected, but extremely important tool in analytic number theory. So mostly I want to also mention what kind of mathematics uses and arises from Poisson summation formula. So the most simple use of it is to understand exponential sums. So what is an exponential sum? Usually, it's just a phase, e2 pi x, and then some functions on phase, so maybe a polynomial with irrational coefficients. And usually, this is something that took me a long time to understand. In a way, the proper way to think about exponential sums is that there's always some associated counting problem behind them. So if you think about exponential sums in finite fields, this is actually explicitly the case, but it's a bit less the case for this. Okay, and so how do exponential sums relate to counting problems? So maybe here's a way of seeing this relationship. So let's say that I want to count the number of solutions to, in how many ways I can write n as a sum of these Vth powers, okay? So one way that you can express this type of counting, you can express it in terms of exponential sums. So you can take an exponential sum e2 pi I alpha xv, raise it to power k. This thing actually is the generating function of the number of solutions to this equation. And then you just extract the h, sorry, this should be n, the nth coefficient, and this is exactly the number of representations of n in this way. So then you see that if you understand this exponential sum very well, you should be able to actually asymptotically evaluate this integral and then answer this question. And this is how this Waring problem is solved in the modern age. So just to give you kind of a benchmark of how well these methods perform, just on probabilistic grounds, you expect that k needs to be v plus 1 for every large enough integer to be represented. What we can do k of size v log v. So we are just a log away from actually a complete resolution of this problem. Okay, and this type of parametrization, we call this circle method. So then, if you want this to work, you have to really analyze this exponential sum, and you analyze it when alpha is close to a rational number and then close to an irrational number, and you get a formula, asymptotic formula for this. But let me give you a more modern example. So let's say I want to count the number of solutions in integers to this type of strange inequality. You see, and alpha is going to be, well, alpha is going to be different from 0 and 1. But think of alpha maybe as something like pi. Okay, think of alpha as irrational, or maybe think of alpha as 3/2. So something a bit unusual. And so I would like to count the number of solutions to this equation. This is a defined time problem. It's a bit unusual. It's not exactly the kind of problem you would see in algebraic geometry. It's a bit more general. We can tolerate exponents that are not integers, for example. And we want to understand how many solutions there are to this. So first, let's do a heuristic to see what to expect. So first, one thing could happen. This integer could be equal to this. This integer could be equal to this. In that case, this whole expression is 0. So it's always less than 1 over x. So you always have n squared solution, no matter what happens. So now there's also another way of looking at this. You could normalize each of these n1s by n. So you could just divide everything by n to the alpha. Then each of these expressions is basically of size 1. It's between 1 and 2 or something like this. And then you can just claim that these are like random points of size 1 and 2 once they're normalized. So if these are just random points, then the number of points that should satisfy this constraint should just be the volume, which means that it should be just the number of choices times the probability that each of these choices fall inside the region. So here there is another typo, which I'm sorry, there should be no 4 here. So I guess this is my way of checking who follows. So whoever nodded in agreement with me, there is no 4 here. It's just the volume, which is n alpha over x, no 4. And so this is the number that we expect. This is the heuristic for this count. And so how do we actually prove such a count? So the first step is to find an integral representation, a way to represent this in an analytic form, not in a combinatorial. So what you do is this: you set up an integral with a 4th power. W is just some smooth function that is kind of like a bit flat from 1 to x. And then this expression here literally just counts the number of solutions where this difference is less than 1 over x. Because if you expand the 4th power and you just integrate over t, you get the Fourier transform of w, and that is simply w hat, x, and this. So this expression is equal to this, and this just picks out where these terms are less than 1 over x. Okay? So I'm putting a smoothing because that's what we do in analytic modern number theory. We always smooth everything, so I don't want to hide this detail from you, in a sense. Okay, and so, so this is a way of setting up this problem. But now how do we proceed from here? Well, one thing that you can notice is that you can apply Poisson summation to this thing inside. You could literally just apply Poisson summation to the sum inside the 4th power. And so if you do this, you get something very beautiful. This n over n to the alpha transforms to n over x to the n with another exponent, alpha squared. And this alpha squared is just alpha over alpha minus 1. So now if you think about it, you can take this expression that you have from Poisson summation, and you can just plug it back into here, and then expand the 4th power and see what you get. And what you get a dual counting problem. So this is very not obvious, right? It turns out that actually this counting problem has a dual counting problem with different exponents, and they are related. And so this, I see no way of seeing this in an elementary way. I think the only way to see this is by using Poisson summation, right? So somehow every counting problem has a Fourier dual counting problem. This is what Poisson summation gives you. So does this make sense? This I'm checking with the dean if he follows. Because okay, so basically we have this I'm saying that we have this integral representation for the counting problem. We apply Poisson summation. It transforms, well, it just gives what it gives. We don't know ahead of time what we're going to receive, but we receive something very nice, and it is so nice that we can just plug it in here, make a little change of variable in t, and then we actually get another counting problem, but in different ranges, right? So you see here you have 1 over x, but here you have some 1 over x tilde. Here the variables are of size n. Here the variables are of size x over n. So something strange has happened, right? And now we're going to try to use this. So if I applied Poisson summation again to this dual problem, I will get back this. So this is a tautology. I cannot just kind of keep applying it. But one thing that you can notice, we can now set up some sort of inductive process. So let's say that I have a bound for this, which I know to be true in some range of x. So you notice that when 1 over x is big, the problem is easy because the volume is large. When 1 over x is small, the problem is hard. So I start with some bound that I have when 1 over x is large. Let's say it's an easy bound just by integration. So then, okay. So then, okay, now we want to shrink this range a little bit. So what I do is that I now try to prove this bound in a slightly more difficult range. What I do there is that I apply Poisson summation to that. I get a dual counting problem. What happens then is that things change a little bit. And to solve this new dual problem, I apply my inductive hypothesis. But I cannot always apply the inductive hypothesis. Sometimes I will need to enlarge this constraint 1 over x bar to something larger, and then I can apply my inductive hypothesis. Okay, and so what you do is that you just do this type of iteration. You start with a range you know, you want to go to a better range, you apply Poisson summation, you get a dual problem. Then to solve that, you apply your inductive hypothesis. But you possibly enlarge a little bit the counting, and then you apply it. And then you keep proceeding in this way inductively until you're actually able to get optimal bounds in all ranges. Okay, so this maybe doesn't make fully sense because this is actually quite technical, and I'm trying to summarize something quite technical very briefly. But this is one way in which we use Poisson summation in the modern times. So we set up this type of inductions between counting problems. And so this specific bound is due to Robert-Sargos, but it builds on ideas of Bombieri-Ivanec. And maybe to emphasize that I cannot convey all the technical details to you, well, given what I said, you would think that the same thing should work if you had a counting problem with 8 variables, right? Based on my explanation here. But that actually is not going to work. It will not cover all the ranges, it will block. So of course there are some technicalities that I'm sweeping under the rug. So I guess I want to just point out that there is this feedback loop between Poisson summation and counting problem. That when you want to obtain good solutions to counting problem, you frequently go to exponential sums, then you relate the exponential sums back to counting, then you solve there something, and you keep going like this, a bit inductively. And this idea of relating bounds for exponential sums to counting problems, so it really comes from Vinogradov in this context. And those are still the best results we have. And what Vinogradov is interested in, he's interested in bounding these type of sums when f is a very high degree polynomial, right? And now there is something counterintuitive happening here. So you might think if f of n is very high degree polynomial, then this oscillates very quickly. So this should be very random. So we should have very good bounds, right? Because the higher it oscillates, the more random it is. But what happens is that the more it oscillates, the harder it gets, because this is not a continuous problem. This is a discrete problem. So if the oscillation is very high, it means that between 2 consecutive integers, a lot of things can happen. So this is harder to control. It's harder to actually guess that not too many things can happen between consecutive integers. All right. So how does Vinogradov attack? What is his method? What does his method rely on? So he does something that we do a lot in analytic number theory. Instead of trying to bound one individual sum, we try to embed it in a larger family. So the point of this is that when you manage to embed something in a larger average, you can build up structure from having this larger family. You can build up relations between different elements of the family. So what Vinogradov does, he takes this problem and he manages to relate it to this counting problem, essentially. He manages to embed the problem of bounding this into what I call a family, into the problem of bounding an average of many things. And so eventually, in Vinogradov's method, you have to consider these types of expressions. And this is what I call a form of amplification. You assume you kind of embed one object into a family, and then you bound the family. And then, so this is just a counting problem. If you expand the L power and you integrate over everything, you will get a counting problem out of this. And this is known as the Vinogradov mean value theorem, though it should have been known as the Vinogradov mean value conjecture, I suppose, for a long time. And so what is the counting problem is this. You see, you have two L variables, x1, xl, y1 up to yl, all of size n. And then you get k conditions. But this is not linear algebra. These are nonlinear conditions that you get out of this. So the sum of the first powers have to be equal to the sum of the first powers. The sum of the second powers has to be equal to the sum of second powers, and so on. And so what you have to show in this problem, and what is the difficulty, you have to actually exploit this nonlinearity. And you have to show that if you have that few equations can constrain many more variables than in typical linear algebra. So let me put it this way. In this problem, you always have trivial solutions, right? I could just assign x1 equals to y1, xl equals to yl. I could make all the variables pairwise equal, and that would be always a valid solution, right? So I call these solutions diagonal. I have n to the l of them. And what is the point of the Vinogradov mean value theorem? The point is to show that just with a few equations, actually square root of L equations, I can constrain L of them and say that they all have to be equal. So this is very interesting, right? This kind of, and this constraining just comes from the non-linearity. It just comes from the fact that these equations have curvature. So here I kind of emphasize that this is very different from linear algebra. If this was just linear algebra, you would need k equations to constrain k variables. Here you actually want to constrain k equations with square root of k variables. And so Vinogradov, in many ways, he introduced many revolutionary ideas that people rediscovered later in similar contexts. So, for example, he introduced something called a TT star method in number theory, and it was discovered in harmonic analysis only later. And something similar happened here. So Vinogradov actually introduced this problem, and he partially solved it. And then something related was rediscovered in harmonic analysis in the 90s by Tom Wolfe. And this was called decoupling. And so this problem, this counting problem, was recently solved by Bourgain and Demeter Good. And so what they actually used this decoupling approach pioneered by Tom Wolfe. And they managed to obtain optimal bounds for this equation. So before we had somewhat suboptimal bounds from Vinogradov's work, and they managed to get optimal bounds. But they still have not fully surpassed it, by the way, because Vinogradov in his work, he obtains really nice uniformity in K, which they do not. They have to just fix K. And so independently of them, there was earlier work of Woolley, who actually almost fully solved the problem. He covered almost all ranges except a narrow one. And then it turned out that actually the two methods are actually quite similar. So Bourgain and Demeter Good, they use decoupling, and Woolley, he actually uses somehow like a p-adic analog of decoupling, but he didn't know this. So in analytic number theory, we often do things, we do something in elementary ways, and then some people call it sophisticated names in other fields, and we do it even though we don't know it. So, okay, and so now we want to discuss a different aspect of Poisson summation formula. So I just mentioned it in the context of exponential sums, but it has a second life as a trace formula. So Poisson summation, I hope I convinced you, is very useful for us. So you may want to generalize it. And then you might hope for more applications of it. So one way to generalize Poisson summation formula is to see it as a case of a trace formula. So what do you call a trace formula? It's anything that arises from this trivial thing for unitary matrix T, right? So if I have a unitary matrix T, I can compute the trace as an eigenvalue in terms of an orthonormal basis, no matter what it is. And so you can actually recover Poisson summation formula in this context. So your kernel would be basically this. So you would consider this type of kernel. You would first pick a function f. Then you would consider some kind of smoothing of this function f over translates. And then you would build this kernel out of it. And then if you consider things in this way, then you can compute the trace of t as an integration over the diagonal, kxx. This will give you the physical side. And then you can do a spectral expansion in terms of the eigenfunctions. This will give you the dual side of Poisson summation formula. And this kernel, it has a nice property. It depends only on the distance between y and x. And it is periodized to be modulo 1. Right? You take a function f, and you make a periodic function out of it by summing over all integer translates. Okay. So now you ask, and you see this is done in Euclidean space. This is done on the line, on the real line, right? So now we ask, can we generalize this in a non-Euclidean setting, let's say in the setting of hyperbolic geometry? So this is exactly what people have done. This was done by Sauberg. This is somehow the beginning of the Langlands program, the first trace formula. So how does it work? So we consider a hyperbolic space with curvature -1, and then we mod by the action of SL to Z. So these are isometries of the space, these Mobius transformations. And you want to fold the domain, kind of like the analog of the unit interval, right? So you want to fold everything back to a fundamental domain by these isometries. And then you build up a very similar kernel, but you sum over all the isometries of the space here, so you sum over all the gammas. And then you can simply repeat the same construction as we had before. So you can also consider this type of kernel where you integrate k against a function. So now your function would be this. You would integrate over the fundamental domain. And this is the exact hyperbolic analog of this previous construction. And this gives you the Sauberg trace formula, which is pretty non-trivial, and relates the number of closed geodesics on a manifold with its spectral expansion. And then you can work a little bit more, and you get something called Kuznetsov trace formula, which basically relates this type of exponential sums summed over the moduli with the spectrum of the Laplacian. And this is a formula which is abundantly used in analytic number theory. Its unique feature is that it allows you to sum exponential sums over the modulus Q. And this is basically the only the only useful example of such a thing that we have in analytic number theory. And it is really used a lot. So for example, this is just one random application out of many. This is not the most impressive or something. It's just something that came to my mind immediately. So there is, for example, a result of Conry where he shows that 40% of the zeros of the Riemann zeta function lie on the line 1/2. 40% means that if you fix a box, then out of all the zeros in the box, 40% will be on the line. And so an element of the proof is actually the use of this formula there, among other things. And what this formula allows him, it allows him to improve the proportion from 33% to 40%. So, so this is really quite used quite a lot in the subject. Okay, so I focused so far almost exclusively on the Poisson summation formula. So now I want to focus on the other side, the Euler product, and what kind of math we get out of this. So if you look at the Euler product, I want to first convince you it's really tied with the zeros of the Riemann zeta function. These are kind of like dual objects to primes. There is a duality between primes and zeros. So what does the Euler product give you? The Euler product allows you to take the logarithm, right? I can take the logarithm of the zeta function, I get a Dirichlet series, and then I can still differentiate it. So it gives me a formula for zeta prime over zeta, for the logarithmic derivative. One thing that you can do once you have this, you can integrate this and shift a contour, and this allows you to relate a sum over primes with a sum over the poles of this, which are actually zeros of the zeta function. So you get this relationship that primes are actually equal to zeros. But the one thing that changes is that here we weight with a function f, here we weight with f hat. So this formula is somehow limited by the Heisenberg uncertainty principle. You cannot localize, you cannot ask too much information both about the primes and about the zeros. And this is why this formula is maybe not so useful. It's very striking, but you cannot at the same time ask too much about the primes and the zeros. But this is a thinking that we have a lot in the subject. Primes are equivalent to zeros, something that we keep in mind all the time. Okay, so let me start again a bit unconventionally. Instead of focusing on the primes, I'm going to focus on the zeros, and then from there, I'm going to get to the primes. So how do we understand the zeros? The best tool that we have towards this is something called mollifier. So a mollifier is just a finite Dirichlet polynomial, and it has this property that zeta times m of x is mostly 1, outside of zeros. And the existence of such a function is only possible thanks to the Euler product. So what is the point of this function? You see, the point is that if x is very small, then we expect that the complexity of this is somehow truncated too. This is not too complicated of an object. And then if this relationship holds, it means that m of x is somehow like 1 over zeta. So then we can actually, by studying this, we can manage to say something about the zeta function itself. Okay, so let me kind of explain how this is actually used to say something about the zeros. So let's say that I want to show that most of the zeros are very close to the half-line, and that the further you go, the fewer zeros there are there. So one way to accomplish this, the simplest way, is to just do an analog of Jensen's formula. So let's say I want to bound the number of zeros to the right of sigma with imaginary part less than t. Then I can cook up an analog of Jensen's formula, and I can say that this number is bounded by this type of integral. So then you have to bound this integral, and we don't know how to compute the log. So what we do usually, we do Cauchy-Schwarz, and then you have to bound this. Use AMGM, and then you have to bound the square of zeta, which is quite big. It oscillates up and down quite a lot. So you get results which are quite poor. This doesn't work very well. So in other words, you see zeta function goes up and down somehow unpredictably. Because of this, the sign of log is positive and negative, quite unpredictably. So there is a lot of cancellations in this formula, which are hard to detect because we want to take absolute values. We don't want to deal with oscillations. That's difficult for us. So what's the point of a mollifier? We're going to make a gambit. So instead of counting the zeros of zeta, I'm going to count a larger quantity. I'm going to count the zeros of zeta times the mollifier. Right? So at the beginning, I will lose something. But now when I apply Jensen's formula, I have the integral of log of zeta times the mollifier. And I expect this to be close to 1 most of the time, which means that in this formula, I actually don't have as much oscillations. You see? So I sacrifice something at the beginning, but then I have a gain that in my Jensen formula analog, I don't have as much oscillations. So then when you apply AMGM, everything reduces to actually the problem of showing how close on average zeta times m is to 1. And if x is not too large, you can actually solve this problem, and you get very good bounds. You show that somehow the number of zeros away by delta over log t decays exponentially with delta. So, okay, so maybe now, how do you actually minimize this expression, right? So you have zeta times this modifier. It has some random coefficients lambda d. What should these coefficients be? So if you have this, one thing that you can do, you can take Plancherel. You can think of this as a Fourier transform of something. And if you apply Plancherel, you find on the dual side this problem. You have to minimize this type of expression for some t, some u, some x. Not important what it is for us. But one thing that you have is that lambda 1 has to be 1. So basically you find this problem. You have to find coefficients lambda d that on average minimize this type of sum. Okay. So now what are kind of the limitations to this minimization problem? So suppose that x is small. X is something like square root of n. Then if n is prime, then this sum consists of only two terms. It has d equals 1 and it has d equals n. D equals n is too large, so it's not counted. So you only have d equals 1, and this is equal to 1. So it means that on primes, I cannot minimize this expression. But maybe I can reduce it on everything else. So this is kind of what I mentioned. So the best that we can hope for is to find coefficients that minimize this sum of d dividing n on everything except primes. And so this leads you to the topic of sieve theory. So what we do in sieve theory is that we want to construct coefficients lambda d that have this peculiar property, that they are upper bounds for the indicator function of n is prime, and somehow the L1 norm of this is close to the L1 norm of this. So these are purely combinatorial constructions, and you want to keep x somewhat small, because the point of this construction is that this is difficult. This is a difficult object with high complexity. And you want to say that you can upper bound it by an object of small complexity, but that is still actually accurate enough. Not too accurate, but still accurate enough in the sense that somehow the L1 norms are within constant factors, constant multiples of each other. And so this is the topic of sieve theory. And one of its early successes is a result of Viggo Brun. So he shows that if you sum over twin primes, 1 over p over primes that are twin primes, then that sum converges. And this is in contrast to a sum over all primes, which actually diverge. So this was the earliest application of sieve theory. And the modern applications are in the work of Zhang and Maynard, both based on Goldstone-Pilz-Yildirim. So they actually show the existence of bounded gaps between primes, and they do it purely by sieve theory. So their proof is actually elementary. I mean, it's a proof that I could present to undergraduates. But the sieve actually has some, so this is all very nice, but the sieve has a very fundamental limitation. It's something called the parity problem. So the sieve is not able to detect the parity of the number of prime factors of a sequence. So let me kind of give you an example. There is a result of Chen, which says that every even integer is the sum of a prime and an integer that is the product of at most two primes. And this, from the point of view of the sieve, is optimal, because the sieve is not able to enforce that the second integer has exactly two primes. It's always either 1 or 2. And this is the parity problem for the sieve. And maybe another example along these lines. So you have this result of Maynard and Zhang on bounded gaps between primes. And the shortest gap that the sieve can give you is 6. Because what you do is that you consider a polynomial n times n plus 2 plus, I think, n plus 6. And then you want to use the sieve to restrain the number of prime factors. But the sieve can only tell you that it's either 3 or 4. So then the best gap that you get is 6. Okay, I probably did this a bit wrong, but you get the point. Okay, and so this type of result that would show that an integer is exactly the sum of one prime and one integer that has two prime factors, that is beyond the ability of the sieve. So there has been actually a lot of techniques developed to go beyond this abstraction, especially by Iwaniec and Friedlander and collaborators. And what you need to do, you need to insert some additional analytic information into the sieve to kind of overcome this problem. And the most basic information that you need to know the behavior of your sequence of interest on a function called the Liouville function. And it's a function which detects the parity of the number of prime factors. So usually, if you're able to control the parity of the number of prime factors of your sequence, then you can actually augment the sieve and obtain, you can actually overcome this parity problem. So if you want to solve twin primes, you will actually have to solve this parity problem. This will be an unavoidable aspect of this. And so, for example, in the case of twin primes, what the parity problem says, it says that at the very least, you'd want to be able to show that the sequence n plus 2 has equally often an odd and even number of prime factors. So then you can formulate a conjecture about this type of sums, the Liouville function n plus 2. And this function is actually multiplicative. It has this property that lambda n of m is equal to lambda n times lambda m. So you can rewrite the sum in the following way. And then anyway, I mean, you can just, this mean value is known to be 0, so you can actually expect that these are independent. So you'd expect that the sum also tends to 0. So you are led to this conjecture that the sum of lambda n and lambda n plus 2 tends to 0. And you can view this type of estimate as some kind of multiplicative analog of twin primes. That's one way of seeing it. So it's basically a statement about the independence of the prime factorization of n and n plus 2. And so in general, this conjecture is known by the name of Chowla's conjecture. So in general, what you can consider is that if f is an irreducible polynomial, then lambda of f of n tends to 0. And in the special case, when this polynomial factors into linear factors, this is known as Chowla's conjecture. And so finally, I get to mention some results of mine. So one of the first non-trivial results on this conjecture was due to me and Matomaki. In 2016, we managed to get just a little bit of cancellation. So we didn't manage to actually show the conjecture that tends to 0, but we managed to show just that there's a little bit of cancellation, just a non-trivial amount. But actually, so this was not our main result. This was a consequence of something else that I want to mention. So we proved a somewhat stronger result. The result goes like this. You take a function f which is multiplicative, which means that it respects prime factorization. And then the result says that if you take a typical interval, typical short interval of, let's say, a bounded number of integers, so you fix some epsilon, then there is some big S, h, and the result says that typical short intervals are actually close to long intervals, except maybe epsilon x exception. So how do you interpret this result? It's a bit technical. It basically tells you that the prime factorization in a typical short interval is the same as the factorization in a long global interval. So somehow, if you look at local things, they're actually close to global things, okay? So you can also have some kind of weird conspiracies, for example, where globally half of the integers have an even and odd number of prime factors, but actually locally it's always odd, then always even, always odd, and then always even. You cannot have such strange behaviors. So some people think of this as some kind of ergodic theorem. I think you can interpret it in this way, in a suitable context. And then this was actually used to settle this Chowla conjecture. Tao used it, but only in the logarithmic aspect, so only with these weights 1 over n. And now we have this kind of puzzling situation, actually very puzzling situation. So we have the results of Maynard, which give you bounded gaps between primes, and we have basically a result which overcomes the parity conjecture. And then you ask, why don't we have twin primes? And I don't know the answer to this question. So I don't know why we don't have twin primes given these two facts yet. In fact, one thing about this conjecture is that people used to think, so it used to be somehow common knowledge that if you could prove such a bound, you would get twin primes. but this turned out to be false. So somehow this is the limit, we're here at the limit of our knowledge. And so one other place where this work was pretty useful is something called Sarnak conjecture. So this is a conjecture saying that this Liouville function, this is, you can think of this as a typo, does not correlate with any dynamical system of entropy zero. So he's trying to kind of quantify ways in which multiplication is unpredictable by saying that it's not something that can be interpolated by a dynamical system of entropy zero, of topological entropy zero. And so this will be the subject of talks by Kanigovsky, and Mirek will also talk about various kind of non-standards variants of the ergodic theorem. So this involves work on some kind of dynamical generalizations of the prime number theorem. And I will talk about exponential sums in the next workshops. And this is basically all I had to say. And I want to kind of, my point as I want to say was to emphasize that there is this unity in the subject. So it's often said that somehow the subject is a bag of tricks, but I always have this opinion that one person's bag of tricks is another person's conceptual theory. So it just depends on your level of understanding. Maybe for somebody it's a bag of tricks, for me it's actually a theory. I think that this is a subject that really has a theory, and it's also a subject that's very tied together, in the sense that if you make progress on one question, it really kind of percolates like a tsunami everywhere else. So maybe to give you an example of this, I have this very recent work with Liang Yang, and this is a paper that is basically a result in the Langlands program. It shows the non-vanishing of some periods. But the main ideas come from some paper of Ben Green, who was then inspired by my paper with Matomaki. So you see that there is this kind of, the whole subject is actually close together. I don't know if this is always the case, but it's very tied together. For example, if you make progress in exponential sums, so something that, as I said, only uses Poisson summation formula, it will then percolate and give you progress on the zero-free region for the zeta function, which then tells you about zeros, which then tells you about primes, and then you can use this information about primes maybe to say again something about exponential sums. So it always goes in these loops, the whole subject. I think that's the one nice thing about it. All right, so that's all.
So thank you very much for this inspiring talk, and this part will be conducted by Jakub Wyszewski. So
we have plenty of time for questions or comments, and I have a microphone for anyone to ask.
So the root child law would imply primes or not? Like if you don't average logarithmically, but just Cesaro, would it imply primes?
I mean, I think actually if you have strong bounds, strong uniformity, it implies twin primes.
Like you mean the error term? Like
Yeah.
N2?
Then it definitely implies. But the question is something weaker also enough? Mm-hmm. And that is open.
So you mean just small o of 1, or?
Yeah, I mean, ideally, I'm kind of wondering. So okay, if you just have that, that's probably not enough. But if you have some additional construction from the sieve theory, I mean, morally it should be enough. Mm-hmm. But I think nobody knows how to actually execute this.
All right, thanks.
Okay, thank you. Any more questions? So I have a question about Vinogradov's theorem. So when you look at those systems of equations,
okay. So should I?
Power equations, yes, perhaps you can. I'm wondering to what extent this can be generalized. So you could think of an arbitrary, algebraic set, which perhaps contains in a fine space of high dimension. Is there anything known, or are there any conjectures?
Well, I'll tell you, there's something a bit perverse in the sense that when Bourgain, Demeter Good solved this problem, they did not solve it for integers. They solved it for something more general. So they managed to solve this problem for any set of well-spaced points. So if you replace integers by just points that are well-spaced by, let's say, 1/100, and then you set up the same problem, then they're able to resolve it. And this, and in general, their solution in terms of decoupling is a statement about basically Fourier series, or maybe Fourier transforms. So it's actually very general. So I think, I mean, I don't know exactly what you have in mind, but I think the answer is probably yes. That it can be generalized quite a lot.
Any more questions? Or comments?
So thank you very much. I had the impression that
thank you.
starting from very general and important problems, that you showed in a very simple way, then you led us to big theories with difficult technical problems, and I think that we advise all the participants who would like to learn more to the workshops and to the lectures given by you free. Yeah. So I hope that you will benefit from it, and I hope that it will not be, as far as I know, it's not the first lecture at the Agilent University of yours, and hopefully also not your last turning up here at the university. So thank you very much. Thank you very much.